Like the theme music.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the ebook series. And I'm super happy to have ebook author Steve Howell with us today. Hi, Steve.
Hi, Frank. How are you? Nice to be here.
I'm doing really great on this December 3rd of 2021. And 2021 sort of zipped by kind of quick, I think. In some respects, other respects kind of lingered for a while. But I'm in Phoenix and we're getting sort of our nice winter weather in Phoenix. So we get a lot of the Canadian snowbirds coming down, the 50-degree F in the morning, and then we'll warm up to about low 80s by the midday. And Steve, where are you located at?
I'm actually, today I'm in Tucson, Arizona. So I'm just down the road from you.
Down the road from you.
Yeah, I was going to be in the Bay Area, but it turns out I got a cheap flight. It's my son's birthday, and so I flew down for the weekend.
That is so awesome. That is so awesome. Yeah, and actually I was in Santa Barbara yesterday.
Oh, great.
I flew back into Phoenix last night to come and do these. So very cool. So I won't ask if it's snowing in Tucson because it's not.
No, I think the closest we get is like Phoenix, the snowbirds. That's it.
Right. That is a very awesome behind you. You've got a lot of boxed. What
it
are
is.
those?
These are my son is there's a wall here of Marvel people, Marvel superheroes and things like that. That's one of his sort of big hobbies in life, and I think one of them is Batman and one of them is a Joker, and other than that I don't really know the rest of them.
But I do know in about 20 years, if those things stay in the box, they're going to be worth something pretty. So
that's his hope. I think it's his retirement plan. Yeah.
I like superhero retirement plans. That's pretty cool. Very good. Very good. That is awesome. Steve, what do you like to do for research?
For research, I'm primarily, I think, an instrumentalist at heart who likes to think about building instruments that do something that hasn't been done, or take instruments that are working and try to challenge them to do something at the limits of their abilities. So, as we're going to talk a little later about Kepler, that's what really got me initially interested in Kepler long before it was actually launched. But
So when did you first get into this mission that became known as Kepler?
Oh, wow. Probably about 5 to 10 years before it was launched.
Okay.
The mission PI, Bill Barucki, was putting together people in the US and the world that knew how to do really precise photometry with digital detectors. Mm-hmm. And so there were 3 or 4 of us in the US who had been working on various aspects of that with stars and galaxies. And we were just sort of thinking about in our own little worlds, boy, if we could get one of these CCDs in space, wouldn't that be really cool? You could get rid of the Earth's atmosphere, which is such a drag for doing precise measurements. And so this was a dream for us. And so we all signed on, and the rest, they say, is history.
There we go. And we're going to cover that a little bit in this fantastic ebook. So we'll go ahead and bring that up. And
there it is.
Kepler Mission. And, Steve, why don't you go ahead and take us away?
Sure. So this book is, as you can see, it's edited by me. So when I first was asked to write this book, I thought about writing it all myself. But one of the things that was really important about Kepler, and one of the things that I appreciated greatly when I was the project scientist for Kepler, was that we had so many people in the astronomical community around the world. Some of them were called official team members, and others were just researchers around the world that were more or less team members. And there was so much expertise in the details from the pixels to the science. And so while some of that expertise lied in me, and some of the projects in here and some of the articles in here were helped along and written by me, there's just an enormous amount of information that were stored. And so I invited a lot of people to join in writing this. So I think one of the great things about the book is it's written by the people that actually did the work, people that actually did the science. So everything in here is, sort of their journeys. And so you get to read about each of our journeys, from photometry and observations that none of us dreamed of to the amazing science that we could get out of it.
Very cool.
Now, I should say something about the cover. While we're here on the cover, I'll just add a little tidbit for your listeners and your viewers. So this was not my first choice of an image for the cover. Okay. I had 3 other choices that were, I think, a bit more colorful and fancy, but IOP told me that they can't put those on the cover because of various either copyright issues or multicolor cover issue things. And so I can't quite remember where this image came from. I'm sure it says in the book, but in the end, I actually really like it. I think it's kind of a fun little mission of a sort of a mock of the Kepler spacecraft and bunches of planets out there.
Yeah, going around. How long did it take? Once the idea was pitched, or you pitched the idea, or it was pitched to you on let's do an ebook. How long did that take to get to the final product? Probably maybe a week or 2.
Yeah, a week or 2. Yeah. I think it was something like a year and a half from, hey, we have this idea, maybe you could write this book on Kepler, to here's the finished product. And it was quite a busy year and a half. I probably spent 25 to 50% of my time on the project over that time. And I'm sure many of the authors in here spent a lot of their time on it as well. So, but in the end, it's one of those things where a year out, it's a great idea. While you're doing it, you hate it. And then when it's over, you think, wow, I'm so glad I did that.
Yes. It reminds me of bicycle riding, when you're rolling, and, the phrase is that misery turns to adventure after a hot shower and a cold beer.
That's right. I actually enjoyed the writing of it very much, and being able to reconnect with a lot of my colleagues. So it was really great.
Let's see if we can find out. There's the editorial board. Probably Steve Caller approached you there. Let's see if we get who that cover image is on.
Yeah, it must. Oh, there it is. Right at the bottom of that page. Yeah.
Oh, cover image. Cheers. Yeah. Stencil and rudder. Very cool. So, NASA.
Yeah.
Very nice. And then the thanking. And so let's walk through some of the contents of this ebook.
Sure. So what my idea was, which I talked to everybody on the writing team about, was to try to put this in order of topical orders and perspectives. And so the first part here, which is about the Kepler spacecraft and the mission, has a lot of contributions in it from the spacecraft engineers at Ball Aerospace.
Nice.
And I learned a lot. If you're ever on a space mission, you learn a lot about things you never thought you would care about or ever learn a lot about. And I'll give you an example. I remember a 3-hour discussion. It started with a talk and then a discussion about batteries that are used in spacecrafts.
Okay.
At Ball Aerospace. And I never thought I would talk about batteries for 3 hours. And I have to say that the thing that I remember at the end of that conversation from all the engineers that told me how to use and not use batteries on spacecraft was that you put batteries on spacecraft, but you should actually never use them. And I said, well, why do we put them there? Well, just in case, but you really never want to use your batteries. And so the idea, of course, is you get all your power from the solar panels,
right?
And you don't really ever want to use your batteries because something must be bad if you need to use your batteries.
Something's on life support here.
Yeah, and so things like that, or things about explosive bolts, and just really interesting stuff. But you learn a lot of stuff that's not really astronomy. I never learned in graduate school. So the first part here on the spacecraft is really fascinating to me. And how it operated, and of course the great transition from Kepler to K2 when the reaction wheels on the Kepler spacecraft broke. 2 of them broke, and not only was it the correct 2, because if it was not those 2, the K2 mission wouldn't have worked. So it wasn't just any 2; it had to be only 2 could break, and had to be the right 2 that could break.
You got lucky.
Yeah. Anyway, so it's a really great thing, and to think that the entire K2 mission pointed at fields of view and worked because of solar pressure, not flares, but light, using sunlight to hold the telescope in position. It's really quite a fascinating story. So that's an interesting chapter that won't tell you a lot about the science, but it'll tell you how we did all the science, how we were enabled to do it.
Kind of became an experiment in solar.
Oh, absolutely. I mean, this was clearly an experiment for spacecraft engineers. Yeah. How do you do this? And in fact, you could now launch a spacecraft and only put on 2 reaction wheels and do this technique. Of course, nobody in their right mind would ever do it, but we now know how to do it. So that was pretty cool. So then we kind of divided the science up after that in sections on exoplanets, on stellar astrophysics, on planetary science, so stuff in our own solar system, and then on extragalactic science. And that was sort of a natural divide between people's science expertise and various aspects of it. And one of the things, as you know, if you open new windows in science with new instruments or with new techniques or new telescopes, every time you do that, you find a lot of stuff you don't expect.
Right.
And so while we found tons of things about exoplanets we didn't expect, like, wow, there's a lot of them out there, and oh, most of them aren't a size of any planet we know anything about. So that was pretty fun. We also learned a lot of ways you could take detailed staring photometric time series of stars, comets, asteroids, planets, and Seyfert galaxies and learn a lot about them as well.
Right.
And so the story here really reveals a lot of, I think, our awe and amazement and a steep learning curve over the years of the mission, from you can't study that. Oh, wait, yes, you can. Oh, wait, look how cool you can do. Oh, wait, look at the great result I have. Yeah. And so there's a lot of that in each of these stories. We kind of tell this over and over by the people that, you know, sort of did those various techniques and learned to get to the end product.
Nice.
And of course, those techniques are now being used with TESS.
Right.
With the TESS mission, the same things. And TESS has astrophysics and extragalactic objects and supernovae and planetary stuff, in addition to all its exoplanet work. And that will certainly be true with Plato as well when that comes along.
Right. Connie and company.
Yeah. So, you know, we could go through every figure in this book because every one is a gem and a highlight to do. And so I don't think we should do that. Just saying we should.
I think we should show one. I want to show this cornfield.
So the corn maze, this is a great story. So there was a year when corn mazes across the United States, there's a network of corn mazes, which I didn't know. They all picked a NASA mission to do their corn maze. And they tried to pick a mission that was from a NASA center that was close to where they are located.
Okay.
So this corn maze is located in north central California, out by where I-5 cuts through the middle of nowhere in some people's views, near Stockton. And this was at the Deloso Farms, and they cut this beautiful Kepler corn maze into a cornfield, and then you could walk through it, of course. And it was quite, I mean, this you can't really tell the size here, but this is many acres of corn maze. It took about an hour to go through the whole thing. And a bunch of us were out there from the Kepler project for the opening of the corn maze, and we gave talks. And I was somewhere near the words Kepler there, and I thought it'd be fun to kind of walk around the letters Kepler. And all of a sudden I realized I had 10 minutes to get back to give a talk. And so I did something you should never do in corn mazes. I cut straight through the corn. I just knew if I kept running, I would get to the edge eventually, and I couldn't take my time to figure out my path back there. And fortunately, it wasn't a maze made of bricks or made of hay bales or something. You could actually walk through the corn without breaking them too badly. But when I showed up to give my talk, I had pieces of corn stuck in me all over. It was pretty funny.
I'm pretty amazed at the precision with which they cut these in.
It is, you know, and it's done with sort of a computer program and a tractor that nobody is in. And I think somebody rides in it in case it goes haywire, but basically it does all this itself. It's pretty cool.
Very nice.
Yeah, it's kind of just like a CAD drawing, you know, to make a part. Yeah, so it does that.
Let the computer rip. Very nice.
Yeah. So that was pretty fun. So that corn maze is not that one, but every year they have some great corn maze, and they haven't redone Kepler and probably won't, but it's pretty fun.
Let's talk about some of the primary drivers, at least as far as I understand. It originally was exoplanets. So maybe
absolutely
some of that Earth 2.0.
Yeah, so you know that sort of became the goal, right? I think once we started realizing that there's lots of relatively small planets, I think we were all much more excited about finding something that could be like the Earth. I remember when the proposal was being submitted, one of the things we all had to worry about was could we convince NASA to build this spacecraft and launch it and operate it if the result was going to be that we would look at a bunch of stars and find nothing? And of course, none of us truly believed we would find nothing, but we had no proof that we would find anything. Right. And so, that was a daunting task, but basically it's, well, if you don't look, you're not going to find anything. And you say that in a fancy way with a lot of charts and graphs, and and you can convince people. But as it turned out, of course, we had no trouble finding lots of planets. There's 4,300 from Kepler and K2 alone, or something like that. I mean, they're everywhere, right? Is the new mantra. Yep. And of course, once you start doing that and you start realizing that small planets are more plentiful than large planets, then you really start getting more excited about the possibility of finding small planets that could be in the habitable zone, that could harbor life. And, there was a number of those that came out of the Kepler mission. Now, people always ask me, were there any that were like the Earth? And boy, Earth-like is such a hard term, right? I mean, what does Earth-like mean?
What do you mean by that?
Yeah, is it the size? Does it mean it has to have sequoia trees? Do you have to have, do you have to have a continent called South America? I mean, how Earth-like do you need to be Earth-like, right? So my personal feeling is, I think there are clearly other planets that probably have life. Did Kepler find any of those? I think the answer is we don't know. And of course, science goes on, and we have to keep looking and now, prove the existence of something that could tell us about life. But there are many good candidates. The K2 mission found many other good candidates. TESS has found many, many good candidates. So I think most of us are all very excited now, and hope that we'll see this in our careers, of some 6-meter type telescope that's going to be launched that might actually image some planet, and see something that looks green and blue, or see something that has, signatures of life or water or something like that. So, so that's what the decadal means to a lot of us, right? Is that the green light has been given to, let's go do that. And so we have, 20 or 30 years to go before that's going to all happen, but we're getting closer. Yeah. So anyway, the planets were great. And as you know, when you start looking for things and you find them, they're never exactly what you think about.
You're going to get it. Yep.
Yeah. So a statement, nobody in science ever likes to use the words none or all or never, right? I mean, those are really hard words to use. Right. So I'll try to say this statement without those bad words.
Okay.
There was probably not a solar system we found. We found many multiple planet systems. There was probably not a solar system found that looked anything like our solar system. It's just absolutely nothing like ours, right? We have 4 small planets that we used to think were very close to our star. Well, Kepler found so many planets that are inside the orbit of Mercury, it just blew us away, right? That our solar system is very different in that sense.
The hot Jupiter.
Of course, and hot Jupiters, absolutely, Frank. Hot Jupiters, we don't have any of those either. And if you want to see if solar systems have ice giants like Jupiter or Saturn, well, again, Kepler is unlikely to be your mission for that, because those objects orbit the sun so slowly that you only get, in your 4-year mission, what are your chances of seeing a Jupiter with a 12-year orbital period, let's say, right. and it has to be perfectly aligned, right, to a very precise thing, because its orbit so far away from the sun.
Right. Yep.
So it's not surprising we didn't, but I think that the evidence is clear that there are multiple planet solar systems out there, by the hundreds, by the thousands, probably, right? All over the local galaxy, and of course the whole universe, but in our local galaxy. So I think that Kepler was a rousing success from the point that exoplanets are everywhere, of all sizes, of all kinds, of all varieties, and our solar system is one kind as well. Right.
That diversity of solar systems really exploded.
Yeah, absolutely. Yeah, and it was there was a lot of head scratching about what could that mean? What could that mean? Things like circumbinary planets, right, that orbit a binary star. I mean, who would think about that? I remember theorists arguing with us when we tried to make that claim, telling us that can't exist. I have a theory here.
Unstable to go away, boop, like that. That's right.
Yeah, and I've always been an observer, and I've always thought that observations are kind of some truth, right? There's interpretation and biases, don't get me wrong, but there's some truth there, right? And so if I have this truth and you're telling me as a theorist it doesn't work, well, I don't know what to tell you.
It's very much like experiments, right? I mean,
absolutely.
At the end of the day, astronomy and physics are observational experimental sciences.
Yep. Anyway, and so, now everybody buys into them, and there are many of them known. And so they're just another part of the mystery of oddball solar systems and stuff like that. So
do me a little favor and talk about the relationship between citizen science projects in Kepler. We got a little bit there on the exoplanet.
Sure. Yeah, that's a very lovely relationship. And as you know, it's still going strong with TESS as well. And my suspicion is it'll go strong for the rest of our lives, because there are certainly very talented, dedicated, intelligent citizens. Citizens being people that we wouldn't say are formally astronomers or something like that. But there's also many astronomers that are involved in these projects as well. And they're just called citizen science because they're things that are done with the help of non-official astronomers or something. But what they would do is they would latch on to projects that the official Kepler mission wasn't doing. So, for example, one of our mantras from the early part of the mission was we wouldn't even consider a planet to be possibly a good candidate without 3 transits.
Okay.
Right? Because you can have sunspots, you can have cosmic rays, whatever, right? And those 3 transits, of course, give you 2 sets that are have a period between them, and so that period has to be the same, and the shape has to be the same, and there's a lot of good reason, scientifically, to have a really strong case like that. But Kepler did find systems that only showed 1 transit and systems that only showed 2 transits. And so while we knew about them and we put all that data out in the public, our official mission didn't necessarily follow those up. So there's some really great low-hanging fruit for people to jump onto and do, right? There were also people that would take light curves and search them with different algorithms that the project did to try to find transit in different ways.
Yeah, right.
Circumbinary planets, for example, are very difficult to find with a static transit model, because they don't have a transit that is absolutely periodic. You have a transit that orbits 2 stars, and of course those 2 stars are moving as well. And so the transits come in very odd patterns, which takes a while to figure out, but sort of really confuses an algorithm, a software algorithm that's looking for a periodic single transit. So there's a lot of opportunity, and they also, of course, moved into doing things in non-exoplanet science as well, with pulsating variables and cataclysmic binaries and many things like that. So this is a nice homage to them in the book, and I think it talks about a lot of the neat stuff they did and discovered themselves. And I'm glad it was in there.
Very cool. And speaking of, since we hit upon some stellar objects there, then we move into chapter 4, and we I think certainly one of the surprises coming out of Kepler was how much stellar astrophysics you could get out of that precision photometry.
Yeah, absolutely. I mean, astroseismology was always a thing from the very beginning that we knew we would get, because people had done this from the ground before using things like the Whole Earth telescope. Right. And so we knew we could do it. And if you just looked at the time series and the precision that Kepler would give you, it just would make you, as a seismologist, your mouth would just water. Right. And it turned out, of course, all that's true and even better. Right. Because you now start finding more signals and you refine your techniques, and you can just do all sorts of great things you never thought you could do. So seismology of all sorts of objects, stars like the sun, white dwarfs, things that were on the supergiant and giant branch, those just were kind of a given from the start, and it all kind of panned out and worked out. But I think that these other things like eclipsing binaries, we didn't realize not only how many you'd find, but we've known about eclipsing binaries as astronomers for a long time, but you don't know about this many in this sample, and the diversity and the precision of your light curves. Star clusters, that was a tricky one at first, because star clusters are concentrations of stars, of course, and Kepler had very big pixels.
Right.
And so if you put a bunch of stars close together with big pixels, there's a lot of confusion.
Mm-hmm.
And so that took some doing by a lot of very dedicated people to figure out how to take these giant masses of pixels from the Kepler imaging camera and do photometry of all these stars, some of them which were very detailed, blended with other stars, and use a lot of ground-based work to kind of figure out where the stars really should be, then use the Kepler data to give you very good precision on those. Yeah. And the last thing here is just kind of a fun little thing about the detections of what we learned about various kinds of stars. And that section alone could have been its own whole book to talk about all the various kinds of variable stars and weirdly pulsating things, such as like the heartbeat star is one of these things that came out of the Kepler mission. I should have worn my heartbeat star or t-shirt today. Yeah, I could have shown you that. But anyway, so those are one of the great things that came out as well. And I think astrophysics here, to me, was kind of a natural, because we all knew from the ground that you could look at things that vary. But when you do that so much more precisely and for years and years, you can obviously learn a lot more.
Mm-hmm. Very cool. And I think probably a lot of people knew it was going after exoplanets and hence the host stars around them, but perhaps less well known was the solar system stuff.
Yeah, this really happened with K2, because if your readers don't know, K2, because of the way the spacecraft had to point, it could point basically only into the zodiac. And so if you point into the zodiac, you spend some time crossing the solar system plane. And when you do that, whether you like it or not, solar system planets and comets and asteroids cross your field of view. And so for the solar system interested astronomers, this was a boon. They just couldn't believe we were actually doing this. And so there was just so much work that was done on these sort of interlopers. There's this kind of long-standing story that, observational astronomers, if you love stars, you hate the solar system because they just get in your way. And if you love solar system objects, you hate galaxies because they take all the dark time. I mean, so there's just these battles between observers, and it's funny that we notice those same kinds of things happen here a little bit. I mean, they're all friendly battles, but you have to allocate pixels. And so you'd say, well, how many pixels can I allocate for this comet versus how many pixels can I allocate for this star cluster? There was some, fun little scientific trades off and things like that. So there was a lot of interesting stuff here. And of course, these objects even presented more interesting engineering tasks because they moved across the field of view. They weren't static during the observation like a star or a galaxy. And so if you would watch the images and make a movie out of any of the sequences of images, you would just see asteroids streaking across the images constantly. And they don't go very fast. Some take 2 or 3 days to go across. Some take a month to go across, depending on their orbits and where you're seeing them. So it really added a lot of complexity, but a lot of interesting science that wasn't available before. And I should point out that Pluto was observed. I pointed out because Pluto is my favorite planet. And so we did observe Pluto.
He called it a planet.
I call it a planet. I always will. I have a t-shirt that my father, before he passed away, sent me, and it said, in my time, the solar system had 9 planets.
Yeah.
And so it's kind of fun.
Yeah, I trudged through the snow as well and all that.
Yeah.
As long as we're on this topic, and this is probably a naive question on my part, such as a theorist. Were there TOOs on Kepler? Was there target opportunity stuff?
There were target of opportunities on there, and they were done kind of in a couple ways. One was that you could sit on a target that you thought might do something during one of our so-called campaigns. And, sometimes it did and sometimes it didn't. There was no real way to observe, to change the pixels you were bringing down from the spacecraft quickly.
Right.
So there wasn't that sort of a target of opportunity, but there were things where we would sit on an object that during that time might have something happen to it.
I think we catch a little bit of that on transients towards the end.
Yeah, absolutely. Yeah.
And as long as we're battling between solar system and the extragalactic, we move into the extragalactic and things
Yeah.
people
Well,
did.
one thing we didn't have bright time and dark time on Kepler. It was all just time. Although it is funny, there were times when you looked into the plane of the solar system where the background zodiacal light was quite noticeable. So the whole background of your image would raise up a number of counts when you look, because of the reflected off the dust when you were looking in the zodiac. And so there was kind of solar system time and then out of the solar system time, which is sort of akin to bright time and dark time on a telescope. Yeah, so here the big objects here were sort of active galaxies and quasars, things that were known for decades and decades from the ground to vary, but you could now sample them in longer times and with higher precision, and many more of them simultaneously. So this turned out to be a real boon. And of course, one of the sort of, I think, unsuspecting things, but one of the maybe great legacies of Kepler, which is continuing on also with TESS, is the observation of supernovae. You could observe galaxies. And in fact, this later became something people would propose. You would look at a galaxy and just hope a supernova was going to happen. And of course, you never know where, but if you look at enough galaxies, some of them will have a supernova. And so you would see the supernova, well, you'd see the galaxy before the supernova erupted. You would see the very first, turn on, the very first hours of turn on of that explosion. And that allowed a lot of modeling of what the progenitors were, modeling that hadn't been done before, because from the ground, you usually don't notice a supernova until it's bright. And here we would, in the post data processing, we would say, oh, we found a supernova, and you just go back in time and then you'd see it when it just started getting bright. So this is a really interesting thing, which I'm glad to see that TESS is continuing as well. And a lot of interesting model interaction work here, and a lot of different theories and that to see what these progenitors really are that blow up in supernovae. And of course, once you look at anything hard enough, you realize there's not one kind of thing that explodes. There's not two, there's not three, right? There's a many kinds, and they all don't look alike. And what does it all mean? And yeah, it's awful complicated after a while.
I pine for the simpler days when there was only two types of supernovae, and now we have this zoology of 1CXDs and
That's right. Yeah. And so, sometimes it seems like you're almost going backwards in your learning process, but it's all good.
That's how it happens. Very cool. Very cool.
So one of the things in here we kind of glossed over, and I'm trying to remember if I can see it. I think it's up near the beginning, is I asked some people that weren't really exoplanet scientists or Kepler scientists to write about kind of what this means to them as kind of a citizen of the Earth, or a person who wasn't a scientist. What did the Kepler mission mean? And there's a really nice article in here on sort of how Kepler influenced science fiction. And I would encourage people, if you read nothing else really, if you're interested in just that aspect of it, to look at that little part about how Kepler really tried to influence science fiction. And for me, one of the fascinations was that Johannes Kepler himself probably wrote the first science fiction story, which got him into a lot of trouble, of course, and things like that. But and his mother in particular got her into a lot of trouble. But anyway, it's really nice here. Yeah. So this thing that was mostly by Dave Summers. So it's really a nice little one of these box things. I tried to put these little boxes in of interesting little tidbits of people's personal stories and interactions with Kepler data.
It's all about people. Yep.
Yeah, so that's just a fun little read. It goes into some detail of early science fiction and some detail of later science fiction. But again, it talks about Kepler's book himself writing about science fiction of a witch that sent people to the moon. So
yeah, I'm going to carry it on. Chappelli, Flammarion, etc. Lovecraft, very nice. Wow, that's a big box.
Yeah. This one got kind of long, but
that's a big box.
we had plenty of pages, so that's okay.
With references, this is awesome. Very cool. Very cool.
Yeah. So overall, it's a wonderful wonderful document, and I can't thank all my co-authors enough for spending a lot of their free time for doing this. I also might point out that I hope we have set a trend here that any of the proceeds that come from this book go to the AAS Education Fund.
Oh, that is very nice.
We have decided that's a good thing for us to do with proceeds from this particular book. You know, we all benefited by being educated and going into STEM fields, and for us, this is, you know, a great contribution back.
Yep, giving back. Very nice. Well, Steve, thank you so much for walking us through this, which will probably be an important documentation on Kepler mission.
Thanks very much. It was fun to chat about it and very fun to do.
Cool. And you touched on this a little bit. So let's take a look at the future.
Okay.
You know, you mentioned TESS a couple times. Plato is coming up. We just had the decadal survey come on out. And so where is the future? Is there going to be a Kepler 2, a Kepler 3, or, you know, or you know, Kepler's progeny, you know, of what was learned and what to do better, and maybe the next US led seismology type mission, exoplanet mission. So talk a little bit about the future. Where does the community go over, let's say, the next 5-10 years?
Yes, yeah, sure. So the community is happy to say quite large, and much younger than me is their average age. And so I'm very excited about both of those facts. I mean, we don't want only old people doing this, right?
No.
And the future is for the young, right? So the decadal survey was very happy reading for all of us, because we all had made predictions of that it would love exoplanets, and it does, and it would love that we would learn more about them. So there was clearly preference in there, and, you know, support for something like a 6-meter space telescope that's going to have as one of its main goals either imaging and or getting spectra of planets that could be habitable, planets that are terrestrial, so they're rocky things. So that is already, people had already started on that, of course, but now we have the green light that, you know, funding will magically start appearing. We have JWST that's launching in a week or something, a week and a half or something. We hope to get a lot of atmospheric measurements from JWST with spectroscopy. There will be some imaging, but it will be sort of far away planets, things like very large young Jupiters orbiting at thousands of AUs from their stars. There won't be pictures of Earths, so we won't have that from JWST, sadly. And I think, you know, future missions like the European mission Plato, which will do more details of transits, the European aerial mission, which the US is part of, where we will get spectroscopy of lots and lots of planets' atmospheres. I think upwards of 1,000 various planetary atmospheres will be measured.
Right.
So I think our future is now, we've left kind of the discovery phase, and I think we've moved quickly now. I think we've had this for about 5 years now, but we're really heading into characterization.
Yeah.
Right. And I think you know, characterization to me always just means it leads you to discovery. These two are just a circle in my mind, because once you start characterizing things, you realize they aren't what you think. And you realize, as we just talked about with supernovae, oh, there's 8 kinds of super Earths. Oh, there's 10 kinds of planets like hot Jupiters, right? And you know, they all have their own stories and all that. And so it leads you back into discovery, which then leads you back to characterization. So I think it's a great cycle to be in. I don't know which one I like best, but they're both fun.
So speaking of cycles, I noticed that you have this really awesome shirt that puts science and cooking together.
Oh,
so talk about that cycle. Where is that?
Yeah, I'll show you.
Very good, very good, very good.
Yeah, so this is I also, one of my other passions is I do scientific cooking, and I've taught some cooking classes at various places, and this one's from the Harvard Cooking School, where we actually teach people not really cooking, just how to boil water or whatever, but we teach them about the science of doing the proper cooking. For example, 2 years ago, we taught a class that was on how do you make a foam. And if you've been to any restaurant, almost everything you get has some version of a foam in it.
Right.
And shaving cream, if some of you shave, you have shaving cream, which is a foam, which I wouldn't eat. But there's different size bubbles, there's different stiffnesses. There's some foams you can cook, there's some foams you can't. If you put some under the broiler, they just go away. Other ones get nice burnt peaks on the top, and you have a lemon meringue pie. Anyway, so the physics of foam actually is quite interesting and involves equations, as you might imagine. It involves science, as you might imagine.
Chemistry.
Yeah, and all sorts of stuff. And so anyway, that's a fun little side passion that is great to do. And you mostly get to eat what you make, even if you mess it up.
I have a great idea for your next ebook. I'm gonna call up Steve. Steve, hey, I got an idea.
I got an idea.
You're rolled. Very cool. Well, Steve, I want to thank you so much for spending some time talking about the past and the future and your interests. It's been really great.
Great. Well, thanks, Frank, and thanks for supporting the WS books.
Yep. And that'll do on this one, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.